Hello there, AP Psychology students. This is Mrs. Mathers coming to you today with a lesson on hearing, then smell, taste, and touch to finish up all of the five senses and where transduction occurs. I'm going to start with a little video today that shows how hearing works.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates three tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Okay, so like with all of our senses, it's something that we don't really, think about it unless something goes wrong. And then when something goes wrong with our senses, we really, really appreciate what we had. So let's start by labeling the ear first of all. So go to the diagram in your packet. These numbers should correspond to that. And let's just talk about the structure of the ear. So first of all, um, the outer ear here is called the pinna. And then the sound travels through the ear canal and it hits the structure here, number 8, the eardrum, also known as the tympanic membrane. This vibrates in response to the sound waves, and those sound waves then go to the middle ear. The middle ear structures are actually called ossicles. Now, we they called them stapes, incus, and malleus. That's what I learned when I was in college. However, the terms more commonly used now are the hammer, number 1, because it looks like a hammer. The anvil also looks like an anvil. And then the stirrups. And the stirrups are these tiny bones right here, which is called the stapes. So these bones then move in response to the movement of the eardrum or the tympanic membrane. They send a message then into the cochlea through this tiny structure here, number 9, called the oval window. So the sound goes through the oval window and into the cochlea, this shell-shaped structure. And then on the next slide, we'll take a look at the basilar membrane. As you saw in the video, there are tiny cilia in there, and this is where transduction of sound occurs. Number 5 here is the auditory nerve. Number 4 are the semicircular canals, and I'll talk about those later. Okay, so how do we perceive pitch? There are actually two theories of pitch. One they talked about on the video, one they did not. So the first one is the place theory of hearing. So if I go back to this picture here, at the very beginning of the cochlea, as you start to unwind, you're going to hear the higher pitched frequencies. As you move near the end of the cochlea, where it's kind of right in the inside of that circle, or maybe shown here, you're going to hear the lower tones. Now, people who have hearing loss might have hearing loss in the higher tones, especially as we get older. That's quite normal. Some people have hearing loss, like I do, in some of the lower tones, which is thought to be an inherited hearing loss. The frequency theory of hearing, however, is the idea that the entire basilar membrane acts like a microphone and vibrates as a whole in response to a sound. So, in reality, both the place theory of hearing and the frequency theory of hearing explain how we hear pitch. So the ear, we have often heard, has something to do with our vestibular sense, which is our sense of balance. If you've ever spun around in a circle numerous times, you notice that you get dizzy, right? Well, the reason why is because of these right here, the semicircular canals. You don't need to worry about these names here, but you do need to know that these canals, they have fluid in them, and they sense our bodily motion. And additionally, they have little tiny calcium type crystals that sense acceleration, gravity, and position. So if we spin quite a bit, sometimes they get kind of confused, and that's why we get that feeling of dizziness. Sometimes when people are older, these otoliths will get stuck in part of the semicircular canals. This happened to my dad, and he woke up one day and he had no sense of balance whatsoever. And they said, well, his crystals were stuck. That's what they called it. It's not the technical term, of course, but what he actually needed to do was hold his head backwards so that gravity would take over and those crystals would kind of get unstuck, and then he retained his sense of balance again. So this is an important structure for balance, one that you should know. Now, how do we locate sounds? This is an important one. We have two ears. Now, someone who only has one ear can actually hear quite well. My mom has just one ear that she can hear from. She actually had a medical procedure done where her left ear was completely damaged and her right ear was fine. But the one thing that she cannot do is locate something like a cordless phone or a cell phone or something like that because she only has the one. So what happens is when you hear a sound, goes to one ear first and then to the other ear. And so if they're right in front of you, it will reach both ears at the same time, or maybe right behind you. But if they're to the right or the left of you, the sound will hit the one ear first, and you'll know that that is the direction that the sound is coming from. So it is a really useful thing, actually. It's something I think that my mom, once she lost the hearing in her left ear, that's the one thing that she has really noticed is that she cannot locate where her sound is. So if she's in a crowd and someone says, "Hey, Barb," she's like, "I don't even look anymore because I don't know where they're coming from." Okay. So that is basically what you need to know about sound. What about hearing loss? There are a couple of kinds of hearing loss. Sometimes the hearing loss is conductive. That means that there's a problem with the ear canal, the eardrum itself. If it has a hole in it that doesn't heal, if it doesn't vibrate correctly. Actually, even if you have too much wax buildup and it pushes up against the tympanic membrane, that can cause a temporary conductive hearing loss. My son actually had that happen to him. He really thought something was wrong with him. And then when he got to the doctor, they're like, yeah, you have like a giant piece of hard wax stuck in your ear. And once they took it out, his hearing was fine. Sometimes the middle ear bones can be impacted, and that will cause a loss in hearing. Nerve-related hearing loss, this is when problems occur in the inner ear or in the auditory nerve itself. This is the kind of hearing loss that my mother has. Because her oval window, which was the pathway to her cochlea, was punctured by an ear washing. It went through and it pressed down all the cilia in the cochlea, and she actually has a constant high-pitched buzz that she hears because of the pressing down of the cilia. Now, problems can also occur and cause sensorineural hearing loss if you have too much exposure to loud sounds. So think of those hairs and think of those constantly being pressed down because of loud sounds. That's sensorineural hearing loss. And then in mixed type, there are going to be problems with any of these areas or a combination of them. What about smell? Man, we know that smell is a powerful sense. So how does smell work? You might recall that smell is the only sense that doesn't pass through the thalamus. In your charts, there is a chart that looks something like this that shows the pathway for smell. So first of all, odor molecules are in the form of chemicals. We smell them, and they reach the olfactory epithelium or cilia at the very top of the nose. And here is where the smell is transduced. So this is where the chemical interacts with the cilia and creates a neural transformation. From the olfactory bulb, which is where the olfactory cilia are, that message goes to the temporal lobe, where we are able to identify smell, and to the limbic system, where we form memories. The amygdala, which are strong memories, and even fear and aggression, and hippocampus. So our smell memories tend to be emotional memories, they tend to be strong memories, and we can recall them very quickly. If we have a smell come to us, especially one that might indicate danger, we will smell it very quickly. So we have about 5 million receptors for smell, and we can detect about 10,000 different smells. And let's go to taste. So we know that taste and smell are closely related, but they are not 100% related. So on our tongue, we have about 10,000 taste buds. In the taste buds, we have something called a taste pore. These taste buds are replaced about every 10 days. So if you burn your tongue on hot pizza or something like that, those taste buds will be replaced. So these capture the chemicals that are taste, and they induce a neural impulse right down here where we have a synapse, and this, of course, is where the transduction occurs. Then the transduction and the neural impulse goes to the parietal lobe, where we can identify the taste. Now, the basic tastes traditionally were thought to be bitter, sour, salty, sweet, and fatty, and umami, which is like a meat-based taste. And traditional thinking was that these were located on particular parts of the tongue. This theory is being challenged somewhat at this point, but nevertheless, this has been a prevailing theory for a long time. Now, when we get to the skin senses, our skin, as we know, has many layers, as you can see indicated by this drawing or this diagram. Under the skin, we have many structures, and actually, they're really quite interesting. We have here hair cells, and we don't actually need to go into all of the details of the skin here. It's interesting to note that we have cells for pressure, we have these cells for sweat, these cells also indicate pressure, and then we have cells higher up for touch, and then free nerve endings for pain and temperature. So all of these go to the parietal lobe, specifically to the somatosensory cortex, and we can respond to them very quickly if we need to, especially if they involve pain. So bottom line, can you identify where transduction occurs for all 5 senses? By now, we have talked about them all, and you should be able to identify them. So one of your study questions is to identify transduction for all 5 senses. I recommend that you go ahead and answer that question while it's fresh in your memory. Thanks for your time. Have a great day.